Hi everyone, welcome to the Ignite classes. Today we are going to revise the fourth chapter of class 12, that is moving charges and magnetism. Moving charges and magnetism. In this chapter, first we had learned what is Lorentz force. Lorentz force. Simply, it is the sum of electric and magnetic force acting on a charge entering a region containing both electric field as well as magnetic field. Okay, so here's that region. So I'm marking the magnetic field going inward in the with this into mark, and here we have electric field also in this direction, and a charge q is entering with velocity v into that region containing both magnetic field and electric field. Then the electric force acting on that charge is QE, and the magnetic force acting on that charge is Q into V cross B. We know that Lorentz force, it is the sum of electric force and the magnetic force. So F that is F Lorentz, that is equal to that, I mean Lorentz force equal to electric force, that is Q into E, plus magnetic force, that is equal to Q into V cross B. Okay, so taking this Q outside, we get Lorentz force, that is equal to Q into E plus V cross B. This is the equation to find the Lorentz force. Okay, then what we had learned, suppose we have only magnetic field in that region, that is no electric field, then the charge Q entering V into this magnetic field, it is homogeneous magnetic field. Okay, so then F magnetic force, it's equal to Q into V cross B. Here V is perpendicular to magnetic field, so QVB sine 90, sine 90, it is equal to 1, so it is equal to F equal to Q into VB. Okay, so when the charge Q enters this region with its velocity V, then it performs circular motion. Okay, so this definitely, to maintain this circular motion, there should be a centripetal force, and this centripetal force is provided by this magnetic force. So centripetal force mv square by r, that is required to have this circular motion, is provided by the magnetic force. So a centripetal force equal to magnetic force mv square by r, that is equal to qvb. So we can cut this one v. So what remains? mv by r equal to qb. From this we can find r, that is the radius of that circle. So it is equal to mv by qb. It is very important equation from this section. Note it. Okay. So this portion it's over. Then we learn what's Biot-Savart law. Okay. Biot-Savart law. It's simply there's a current carrying conductor, and we took a region having length L and carrying current I, and it is called current element. We have to find the magnetic field at a distance r from this current element. Then it is equal to dB, that is equal to mu 0 by 4 pi into I dl cross r cap by r square. This is Biot-Savart law. Okay, and after that we learn the magnetic field around, the magnetic force acting on a current carrying loop having current carrying conductor, straight conductor having length L is F equal to I into L cross B. This is the equation to find the magnetic force acting on a current carrying straight conductor. Okay, this is another important equation. Then after that we had learned what's the uh, magnetic field at a distance ax from a circular current carrying loop. This is r, radius of the loop, and this distance it is r, and we have to find, this is dB and this angle is theta. So geometrically this angle again it is theta. We have to find dB cos theta actually, that is the magnetic field acting along the axis of the circular loop. So this is dB, that is equal to mu 0 by 4 pi into IDL cross R cap. Here IDL cross R cap, it means DL cross R cap. It means DL, modulus of DL into modulus of R cap. This is R cap, unit R cap means unit vector. So the modulus of R cap, it's the magnitude of unit vector is 1. So it is DL sine theta. In this case it is sine 90. So IDL by R square. Okay. So from this triangle, that is the one that I drawn before, that is this one. Here R is there, R is there, this is theta and this is x. So from this triangle we have applying the Pythagoras theorem, r square equal to x square plus r square. Okay, so we can apply it here. Here r square become x square plus r square, and we have to find dB parallel. That is, so we have to find cos theta. Cos theta here is r by r, that is r by x square plus r square whole raised to 1 by 2. So we get dB, that is equal to mu 0 by 4 pi into IDL r by x square plus r square whole raised to 3 by 2. Okay, then B equal to mu 0 by 4 pi into I r by x square plus r square whole raised to 3 by 2. Integral dl, it is 2 pi r. Okay, since we are integrating around that circular loop, and we can cut this pi and pi, 2 and 2, then it is 2. So what we get, B equal to mu 0 by 2 pi into I r square by x square plus r square whole raised to 3 by 2 we have. Okay, so B equal to mu 0 by 4 pi into I r square by x square plus r square whole raised to 3 by 2. This is the magnetic field at a distance x from the circular loop having radius r. Suppose this x, we have to find the magnetic field at the center of the loop. That is when x equal to 0. X equal to 0 means at the center. That is, we can cut this x. So what we get, B equal to mu 0 by 4 pi into I r square. In the denominator we have r square raised to 3 by 2. That is r cube. Okay, so by r cube, r square and r cube we can cut, and what remains, we get r. Okay, so here we have B equal to mu 0 by, one more time, mu 0 by 2 into x square plus r square whole raised to 3 by 2, and the numerator we have I r square. So when this, in order to find this, here this is the loop, in order to find, this is that one. So in order to find the magnetic field at the distance x, it's okay. Okay, so this is the equation to find the magnetic field at a distance x, but in this case we have to find the magnetic field at the center of the loop, that is x equal to 0. That's we are doing. So when this is x is 0, what we get, we get B equal to mu 0 I r square by 2 into r square raised to 3 by 2, that I said now, r square raised to 3 by 2, that is what, r cube. So here in the denominator we have r cube, we can cut this r square and r cube, and what remains, we get r. Okay, so B equal to mu 0 I by 2r. This is the equation to find the magnetic field at the center of the current carrying loop. Okay, so this we had learned this too, and after that we learn another special case, that is this current carrying loop, it is the current carrying circular loop, it is the simplest unit of magnetism. Okay, so this is r and this is x. Then suppose this x is very greater than r. Okay, In that case, this current loop carrying this current, itself we can treat it as what? We can treat it as a magnetic dipole. Okay, so we can use the same equation here also. We got that at a distance x, the magnetic field from this circular loop along its axis is mu 0 I r square by 2 into x square plus r square whole raised to 3 by 2. Okay, when x very greater than r, we can neglect this r in the denominator. So what remains? X square raised to 3 by 2. That is, cut this 2 and 2. So we get what? We get x cube in the denominator. So mu 0 I r square by 2 into x cube we get. Okay, so I'm going to have some arrangement. That is, I just multiplied numerator and denominator with pi. That is here 2 pi. Okay, just multiplied it. So what is I into A? I into A, it is equal to M. Magnetic dipole moment equal to I into A. Okay, the magnitude of it is equal to I into A. And so here we have what? B equal to mu 0 by 2 pi. In the numerator IA, that is equal to m we have, so by into m by x cube. So everywhere in the magnetism, starting from Biot-Savart law, we have mu 0 by 4 pi. So in order to make this as 4, just multiply numerator and denominator by 2. So what we get? We got B, that is equal to mu 0 by 4 pi into 2m by x cube. This is the magnetic field due to a dipole along the axis, magnetic dipole. Okay, so here, so we can say this circular current carrying loop acts as a magnetic dipole, and this equation gives the magnetic field along the axis of that dipole. Okay, is along the axis. So we have a in the electrostatics we have electric field. This is the dipole in electrostatic, plus q minus q, and a distance of 2a separating them. Okay, that is the dipole there. So in that case, the suppose this is the distance. So the electric field along the axis, that is equal to 1 by 4 pi epsilon 0 into 2p by, if this distance is x, 2p by x cube there. So along the axis, and in the case of when we are finding the electric field along the axis, so along a direction perpendicular to the dipole, this is dipole plus q and minus q, there the electric field equal to 1 by 4 pi epsilon 0 into p by x cube, where p is the dipole moment. So using this analogy, what will be B? B, the magnetic dipole, the magnetic field along this is along the axis. First we find along the axis, then in a direction perpendicular to the axis, that is in this way. If it is perpendicular to the axis, we have to find the magnetic field along this direction. Then the equation is B equal to mu 0 by 4 pi into p by, simply p by x cube. Okay, so this is in the perpendicular axis, and along the axis I can write it as parallel, otherwise simply p. Along the axis it is equal to mu 0 by, not p, this is in the case of magnetism, it is m, mu 0 by 4 pi into 2m by x cube, where m is the magnetic dipole moment, m equal to I into a. Okay, so that portion is over. And after that, what we had learned? Yes, we had learned this moving coil galvanometer. This is moving coil galvanometer. So galvanometer as ammeter, that is, just suppose this is galvanometer, this is galvanometer resistance, and we have to convert it into ammeter. Just connect a small resistance called shunt resistance, where Rs it is very less than Rg, parallel to this ammeter. Then what we get? we get Rg, effective resistance as Rg into Rs by Rg plus Rs. Since Rs is very small, we can neglect it. So what we get, it is approximately equal to shunt resistance Rs. Okay, and we learned about the structure of this galvanometer, moving coil galvanometer also. So it's a north and south pole, and there's a spring at the center of this cylindrical conductor, placed at the center of this north and south poles. So this is a top view, and when we know that radial magnetic field lines acts on this um, circular, not circular, cylindrical current carrying conductor, and when we pass current through it, what happens? Torque appears in it, and that torque due to magnetic magnetism, that is magnetic torque, that is equal to, that is due to the magnetic radial magnetic field lines that torque occurs. So that magnetic torque equal to NIAB, where NIA equal to what? N. NIAB, and there is a restoring torque due to this spring, that is restoring torque equal to K phi. Restoring torque equal to K phi, and key for uh, this where K is torsional constant and phi is the twist. We call it this K. Another name is distortion per unit twist. So this restoring torque equal to K phi. So the purpose of this restoring torque is to counter the magnetic torque. That is F toe magnetic torque equal to restoring torque. It will balance it. Okay. So NIAB, that is equal to K phi, and from that we get current sensitivity of a galvanometer, that is phi by I equal to NAB by K. It's very important. This is a current sensitivity of galvanometer. So for what we use a galvanometer? We use galvanometer to know the or to detect the presence of the current. We can't use galvanometer as such as ammeter, because when we use a galvanometer directly, it will give even full scale deflection for microampere current in micro range. uh, Even the current in the micro range give full scale deflection for a galvanometer. That's why to convert it into a ammeter, for what we use this ammeter, we use ammeter to measure current. So in order to convert a galvanometer into an ammeter, we what we are doing is we just connect a shunt resistance, that is the one with very low resistance compared to that of galvanometer resistance Rg, parallel to it. Now it can act as ammeter. Okay, because when a current enters this circuit, most of the current pass to the shunt resistance. Okay, the arm having shunt resistance. So this is a way of converting galvanometer to ammeter. We can use galvanometer as voltmeter uh, just by modifying its structure. That is, this is Rg. Just connect a resistance R having very high resistance compared to that of the galvanometer resistance in series with the galvanometer resistance. Then we get what? This voltmeter. This is equal to voltmeter. Okay, so it can act as voltmeter. That is here Rg plus R, that is equal to approximately equal to R, as this Rg is very small compared to capital R. Okay, and already we have NIAB, that is equal to K phi. Okay, so phi, that is equal to NAB by K into I. Okay, so here for a voltmeter, voltage sensitivity comes into play. That is phi by V is the voltage sensitivity. Just divide both sides by V. So from Ohm's law we have V equal to IR. So I by V equal to 1 by R. So this voltage sensitivity, that is equal to NAB by K into I by V. Okay, 1 by R. I by V, that is equal to 1 by R. Okay, so that's all. So we had covered the important portions from this moving charges and magnetism. And one more thing we had learned here is torque. That is the torque acting on a current carrying loop that is placed in between uh, magnetic poles that we had also learned. So here, suppose this is A, B, C, D, then the BC as well as AD portion, they don't contribute because B, the field vector, sorry, the magnetic field lines acting along the magnetic field lines in between these poles as well as the direction of this BC and AD are same. So the angle between them is 0. So F equal to IL cross B equal to ILB sine 0 in that case. So magnetic force acting on BC and AD is 0. But in the case of AB as well as CD, there the magnetic force is ILB. In this case, when we place a current carrying loop in between magnetic, that is when we place a loop in between two magnetic poles, and when we pass current through it, okay, when we pass current through it after placing it in a magnetic field, it will, that conductor will experience a torque. Okay, so that torque we have to find. That torque is equal to what? That torque equal to m cross b, that is mb sine theta. And its analogy in electrostatic is p cross e. Torque acting on a dipole in magnetic field, dipole in electric field. In the case of electrostatic, it is P cross E. These are the things that we had learned in this moving charges and magnetism. So we had covered the entire chapter here. So thank you. If you like this video uh, class, then please press the like button. And if you want to have this type of classes again, in order to get notification, please subscribe to the channel. Okay, thank you.